Okay. Should I begin? So, having learned yesterday that heavy ion collisions produce a low viscosity, strongly coupled fluid, what I want to do now today is turn to experimental observables with which we can study properties of the fluid beyond just how it flows. Before I do, though, Son very nicely yesterday found for me the actual Weisskopf quote, and I'm going to read it to you. But I will set it up. Son and I talked about this yesterday at dinner. So apparently, it started at Vicky Weisskopf's Festschrift when Purcell gave a talk on, which is written up. It's a famous talk. It's written up with the title "Life at Low Reynolds Number." It's a marvelous, marvelous thing to read. If you never have, you should. And in that talk, he basically challenged the theorists in the room, including Weisskopf, to go think about liquids. And a couple of years later, at I. Rabi's Festschrift, Weisskopf was giving a talk, and in effect, he was reporting on his own failure. So here's what Weisskopf said in his own write-up, contributed to the volume in honor of Rabi. Liquids are harder to understand. Assume that a group of intelligent theoretical physicists had lived in closed buildings from birth, such that they never had occasion to see any natural structures. Let us forget that it may be impossible to prevent them to see their own bodies and their inputs and outputs. So Vicky did this much better than I could possibly have imagined. What would they be able to predict from a fundamental knowledge of quantum mechanics? They probably would predict the existence of atoms, of molecules, of solid crystals, both metals and insulators, of gases, but most likely not the existence of liquids. There's the quote. He said it he wrote it. I don't know how he said it. He wrote it much better than I said it yesterday. Okay, but we want to move on beyond just the fact that we have a liquid. How can we probe its properties in other ways? So what is jet quenching? Well, jet quenching is a suite of observables, experimental observables, some of which I will describe, which altogether reveal what happens when, if you could imagine that the thought experiment, not the real experiment, the thought experiment is you have a drop of quark-gluon plasma and you shoot a quark at it. Okay, that's not the way the experiment is done, but the question is what happens when a very energetic quark or gluon with momentum much, much larger than the temperature T of the plasma plows through the plasma. What happens? How much energy is lost? How does the fluid respond to this bullet passing through it? So the way that the experiment is done, where do these high-energy quarks come from? Well, they come from the same collisions in which the plasma is produced. We saw yesterday that in a small fraction of collisions, there are hard scatterings which give you high momentum hadrons. In that 1 in a billion, 1 in a trillion events, at time zero, you have somewhere in the middle of the collision, pancakes collide. In the middle of the collision, there's a hard scattering, which produces a back-to-back pair of quarks, let's say, with, to pick a number, 20 GeV transverse momentum each. If that collision happened in vacuum, so if that happened in a proton-proton collision, those back-to-back pair of quarks will each become a jet, and you get a two-jet event, one jet going this way, one jet going that way. Instead, let's think about what happens in a heavy ion collision. Before I talk about heavy ion collisions, I just want to stress that the rates for these processes, for jet production, if you ask a theorist, a QCD theorist, a standard model theorist, to calculate the rate for the production of, say, 20 GeV pions in proton-proton scatterings, that's something that can be done. It can be done with perturbative QCD. It's not a completely perturbative calculation. The production of you have to take a convolution between some parton distribution function. This doesn't mean PDF-like portable document format. It's a parton distribution function. This tells you how you take two quarks out of the incident protons. So in here is what's the probability of, I have two protons coming at each other, what's the probability that in this one I have a quark with such and such momentum, in that one I have a quark with such and such other momentum. You then have a a hard scattering. And you describe this perturbatively with Feynman diagrams. So this is, say, Q plus Q from the incident protons goes to Q plus Q with each with the 20 GeV PT. And then you have what's called the fragmentation function. And this says, given a 20 GeV quark, what's the probability of finding a 10 GeV pion? This you can all go and calculate. It's a Feynman diagram calculation. Even a string theorist can do it. Okay. This, nobody knows how to calculate, but it's very well measured. And this also, nobody knows how to calculate, but it's very well measured. Okay. And so there is a solid foundation of knowledge which comes from the combination of perturbative QCD plus experiments in which this and this are measured. These experiments are done in proton-proton collisions. So we know then what the probability is of producing a back-to-back pair of quarks in a heavy ion collision, which, if they were in a PP collision, would make, say, a 10 GeV pion. And then what we then ask in a heavy ion collision is, how does this get modified? Now, why do we expect this to get modified? Well, unless this quark, where is it? Unless this quark here is produced at the edge of the fireball and going outwards, before it gets out and turns into pions, this quark is going to have to propagate through 2 Fermis, 5 Fermis, maybe even 10 Fermis of Quark-Gluon plasma. Because this collision, now the PP collision is not happening in isolation. It's in the middle of the heavy ion collision that made that soup. So what we then have is a well-calibrated probe, because we understand, both from experiment and theory to combine, we understand what the probability is of making a quark with a certain energy. And we know how it would turn out in vacuum, and we can see what happens instead. And that will tell us what the effect of the presence of that medium is on that quark that's propagating through it. There are 2 effects if you think about it. So think back to the thought experiment. So I've now told you what the real experiment is. But in the thought experiment, I've shot a quark at suppose I have a brick of Quark-Gluon plasma. I shoot a quark at it. What's going to happen? Well, there are 2 qualitative effects. First of all, it's going to lose energy. And second of all, it's going to pick up transverse momentum. It's going to be, as it's going through this brick, it's going to be kicked transverse to its original direction, and it's going to be slowed down. When I say transverse now, I'm changing the use of the word transverse. Most of the time in particle and nuclear physics, transverse means transverse to the beam. But for the next 45 minutes, transverse will always mean transverse to the initial direction of the hard quark. So how do we know? Well, does this fragment, does anything happen? Does the plasma affect that hard quark? How do we know that something happens? The most pictorial way to see that, the most pictorial use of data to see that something is happening is to do the following experiment. You trigger, and I have to explain what this word means, on, let's say, a charged hadron with, you just have to get used to the fact that PT is used in 2 different ways simultaneously when you talk about jet quenching. Here I mean trigger on the presence of a hadron whose transverse momentum transverse to the beam is bigger than 4 GeV. What does trigger mean? Well, it means that you have a billion events on tape. You look through your sample of a billion events, and you find all of the events in which there's a charged hadron with PT bigger than 4 GeV. That's the theorist's way of thinking about it. Experimentalists are actually smarter than that. A trigger for an experimentalist is a piece of software that decides whether or not to write a particular event to tape. They look in the event for stiff tracks, and we'll preferentially write those to tape. But anyway, we can think of it as you have a trillion events, look through the sample, find the ones with a hard pion. So you now have an event in which so here's, let's say the beam was this way, here's my blob of Quark-Gluon plasma, and by your choice, you have found those events in which there is one hadron with a transverse momentum bigger than 4 GeV, and let's say it's going towards you. Now, you look in that event at, yes. Right. Well, so that's the key is that you're right, and so in fact, some part of the jet quenching will be quenching by the pre-equilibrium stuff, and some part of it will be by quenching by the Quark-Gluon plasma. You don't get to separate that in the data, but this quark, unless it's produced right at the edge going outwards, is going to propagate through the medium for 5 to 10 Fermis, and we saw yesterday that that's much longer than the equilibration time. So I'm going to speak loosely and say it's propagating through the Quark-Gluon plasma, but you're right, that's only true after 1 Fermi. Okay, so what do you look at? You've chosen an event as I described. You then look at all other hadrons in that event, in this event, with, let's say, PT bigger than 2 GeV. Remember that sort of 2 to 3 GeV above there is where you're looking at what we called yesterday hard particles, not part of the thermal distribution, but things that reflect the initial hard scatterings. And there aren't very many of them. It would be nice if you could make this 10 GeV and this 5, but to get statistics, you make that one 4 and this one 2. And you look at these other hadrons in angle phi relative to the first hadron. So in other words, you triggered on an event with a hard particle going towards that gentleman right there. And now you look in the same event and you look at the angle relative to this one. So phi is the angle between this direction and, say, this one. There's another hard particle going off that way. This is the angle phi. There's another hard particle going off that way. This is the angle phi. And you do this in a sample of events, and you make a plot, which I'll show you on a slide half an hour from now, but in the way I've been giving these lectures up to now, doing everything on the chalkboard, here's phi, here's 0 degrees, here's 180 degrees. So 0 degrees means the second hadron is going the same direction as the first, and there is indeed a pile up here. This is a jet. Okay. This says that when you see a 4 GeV hadron, it's part of a jet, and it's likely that there will be other hard particles around it. That 20 GeV quark fragmented into a bunch of hard hadrons. You triggered on one of them, there will be others nearby. So this is the jet. This is a poor man's way of finding a jet. If you do this experiment in proton-proton collisions, then when you look here at 180 degrees, there's some slightly broader, slightly lower distribution. So this is what you see in proton-proton collisions. And this is the away side jet. So remember, the underlying process was back-to-back pair of quarks. That back-to-back pair of quarks in a PP collision became one jet going one way, another jet going the opposite direction in azimuth. Now, what do you see in a heavy ion collision? In a heavy ion collision, sort of cartoon of data, you see some data points which are like this. They come over here, and they go around like this. There's no peak over here. So this is in a gold collision. So you've just discovered that momentum is not conserved. Okay? You've discovered monojets. In a heavy ion collision, you see a jet going out towards you. It's going out that way. We then look on the other side, look for the other jet, and it's not there. So the picture then, if I think in the transverse plane, here's my heavy ion collision. It made stuff which after 1 Fermi is Quark-Gluon plasma, but it made stuff in this region of space. And by triggering, you have preferentially found events in which the hard collision occurred near the edge. Okay, your trigger biases you in favor of finding events like that. So the trigger biases you in favor of events in which you have a jet coming out this way. You then look on the other side, and whatever has happened, there's no jet here. And this is completely different than is seen in proton-proton collisions. It certainly is a sign that the physics of fragmentation is modified by the presence of a medium. And this is the most pictorial way of seeing in the data that jets are quenched. But of course, momentum has to be conserved. So now you do a slightly different measurement. This time you do the same, everything I said before, but this time you look at essentially all hadrons. So it's, again, relative to the same trigger. And when you look at all hadrons, now you're looking at the soft stuff. Most of the hadrons, remember, are down there with transverse momenta of less than a GeV, a couple hundred MeV. Now you do the same thing. Again, for reference, here's the PP. The scales are different now, but I'll just draw it the same way. So this is PP again. This time, again, you get something like this. And this time, you get more than PP. So this time, in gold, and actually I haven't done this quite right. Does someone see the chalkboard eraser? Oh yes, it's on the floor. If this was my PP, what I wanted to do is I wanted to make this go above here and have a slight excess about there and a slight excess about there, but I'm trying to give you the sense that this excess is not very statistically significant. So what you see when you look now, so now what's the experiment now? There's a jet going that way. Now you look on the other side, and so there is a jet going this way as before. But now over on this side, we're looking at all the soft stuff. You can think of this as you're looking at the debris from the Quark-Gluon plasma. So there's an excess of soft particles on the back side here. So what's happened is that the 20 GeV quark that was produced going this way, which would have turned into a jet, instead has become a little extra Quark-Gluon plasma. So what you're seeing then is the medium. We don't know if it's thermalization may be an exaggeration, but the phrase used is quenching, not thermalization. But it's as if the medium is trying to thermalize that jet and has gone a good way towards doing so.
This is just number of particles over some low threshold.
Over here, this is a cartoon. This is. Yeah, this is over a very low threshold. This is over PT over 0.15 GeV. That one was over a relatively high, well, a medium threshold. Okay.
Can you draw on the angular plot where 2 GeV is?
Sorry, just a second. First of all, this is 0 degrees, and this is pi. And I'll note that roughly speaking, these little excesses, these shoulders here are about 2 pi over 3 and 4 pi over 3, just to set scales. What was your question?
Where is
2 GeV doesn't appear on these plots. These are plots in azimuthal angle.
It's a number count.
It's number. This is number. This is just number. Yeah, number of particles as a function of azimuthal angle.
In the upper one, you said you're only including hadrons with the PT.
Bigger than 2 GeV. Right. So this is number of hadrons with PT bigger than 2 GeV, plotted as a function of azimuthal angle relative to the first one.
Oh, I see.
Got it? This is, well, first of all, it's not every collision. It's only the ones in which there was a 4 GeV hadron in the first place. And then this one is a plot of every hadron coming out of the collision, yes. It's actually, this is number of hadrons with PT bigger than 0.15 GeV, which is basically all of them. And that one is number of hadrons with PT bigger than 2 GeV, which is 1 in a million of them.
Why isn't there a sort of background that's independent by just coming from the expansion of the plasma and decay temperature?
Oh, that's subtracted. Sorry.
Sorry?
That's subtracted. Excuse me. Yeah, sorry. You're right. Sorry. You're right. There's a subtract. Very good. And in fact, you actually this one, what you have to subtract is V2. This one is with V2 subtracted. Very important. Yeah, so there's some art actually in, well, art is the wrong word. That's not fair. There's some careful experimental work that has to be done to do the subtraction right, because you're not subtracting a flat background, you're subtracting a cosine. But anyway, let's assume they've done that. So, but that's in fact one of the reasons why this is not such a good observable to get quantitative about. This is a very good pictorial observable, but it's hard to be quantitative about it. So I now want to tell you about the observable that is actually used for making comparisons between data and theory. So this what I've told you so far tells you that jet quenching occurs. But if you'd like to ask quantitative questions, it's easier. People have made quantitative comparisons to two-particle correlation functions like the one I just was describing. What I was just describing was a two-particle correlation function in the experimentalist's sense. But it's easier and more robust against various systematic issues to look at something simpler. But, well, anyway, let me tell you what the simpler thing is, and you'll see that the simpler thing, if I just told you about the simpler thing, you wouldn't be sure that jets were being quenched, and that's why I started here. So the simpler thing comes from the fact that if jets are being quenched, you should see fewer high PT particles. Most 5, 6, 7, 8, 9, 10 GeV hadrons are in jets. If jets are all losing energy, there are going to be fewer of those particles. So the observable that is defined is called RAA, and it's a function of PT, and it is d squared n d pt d eta for a gold-gold collision goes to pi 0 with a certain PT. Divide by, same thing, d squared n dpt d eta for a pp collision produces a pi 0 with a certain PT. So we're not quite done yet, but the idea here is you want to pull out what is the effect of the medium. So you look at the ratio of the number of pi zeros with a certain transverse momentum that are produced in gold-gold collisions divided by that in pp. But obviously what you have to do down here is you have to put the number of pp collisions corresponding to the AA. And there's a little bit of work to do that, but that's work we're going to leave to the experimentalists. And I'll describe to you in a second how we, by reading their papers, can check that they did that work correctly. So we're going to trust but verify. We'll trust for now that they can tell what's the effective number of pp collisions occurring inside a gold-gold collision. And they then construct this ratio. And here's what it looks like. Yeah, this comes from a Glauber calculation. But this time it's a Glauber calculation in a high PT regime, not in a low PT regime. So this time it's a Glauber calculation where I think it's reasonable to trust Glauber. Because for you, the point is that the small x, the wee partons don't make jets. So I think Glauber is correct here. And it's checkable. OK, so here is RAA of PT for pi zeros. The data is from Phoenix. The chalk is all me. There's 1. So 1 would mean no suppression. And here is 0.2, 0.4, 0.6, 0.8, just to show you that I have a linear scale. Linear scale in GeV also. Let's make 2 GeV here, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 GeV here, 4, 6, 8, 10, 10 GeV here. And it basically looks roughly like this. They grow slowly. Something like that. So for PTs bigger than about 4 GeV, you've lost 80% of the hard particles. And roughly speaking, you should think of the 20% you see as coming from the surface. And the error bars do get larger as you go further out, just because statistics get worse. But there's no sign of a dramatic change in this going all the way out to 20 GeV. And so the message here is that in head-on gold, this is for head-on gold collisions. In head-on gold collisions, 80% of the pi zeros with PT bigger than about 4 GeV are missing. Just because that's it's been done with charged hadrons also. It's the same. Phoenix does it with pi zeros because they're very good at detecting pi zeros out to high PT. Star does it with charged pions. They agree. Yeah. No, this is very good. This is I don't remember whether it's -1 to 1 or -0.5 to 0.5. It's some byte of eta, which is about 1 unit wide and is central. Very good. It has to. If you look in the real papers, it's always specified. Okay, but then look at peripheral collisions. So now look at peripheral collisions. So this up here, this was head-on collisions. And for peripheral collisions, here's one, and the data looks, and here's 0.8, and the data looks sort of, here's 2 GeV again, and the data sort of looks like this. There's maybe a hint of a small suppression down here, but basically no suppression. So, loosely speaking, no jet quenching. This is a good sign. It's a good sign that the experimentalists know what they're doing in defining this kind of a thing, because if you do a peripheral collision, you're not making a large volume of stuff. It should be becoming like PP. You can then do an even better control experiment. You can do RAA for photons. So this was RAA for hadrons, for pions. Now you look at high transverse momentum photons. Photons are produced in jets also. When you do a hard scattering which produces a back-to-back pair of quarks, in that fragmentation of quarks there can certainly be photons.
You mean gluons or
Photons. I mean photons. And the nice thing about photons is they don't interact with the medium. So they're a good control. So this is a control experiment. And what you find is that RAA for photons is 1 for all impact parameters. And this really is the control experiment that tells you that the experimentalists are not making some mistake in this factor. Yes, Tom. Yeah, so these are for isolated photons, not pi zeros. Okay. The other control experiment is you do RAA for pions, not in gold-gold experiments, in deuteron-gold collisions. The accelerator physicists have difficulty accelerating protons and gold nuclei at the same time. It has to do with the fact that the charge-to-mass ratio is very, very different. But deuteron has a similar enough charge-to-mass ratio that they can do deuteron-gold collisions. So this, you think of deuteron, you think of as basically it's 2 nucleons. You think of it as having the size of almost like doing proton collisions. And when you do deuteron-gold collisions, you should think of that as I have a pancake being hit by a single proton, by deuteron. So now pancake and deuteron pass through each other, and what I'm left behind, there's no transverse extent to what I'm left behind. So there shouldn't be any jet quenching, and there isn't. This is also 1 for all impact parameters. So jet quenching is not observed in d-gold. So jet quenching is not observed in peripheral collisions. It's not observed for photons. It's not observed in deuteron-gold collisions. It really is something which is characteristic of gold-gold collisions, which are not peripheral. Now, do we know that it is parton energy loss? So what I'm leading you to is the conclusion from experiment that what you are seeing is parton energy loss. Yes. And there's one piece of the logic I haven't said yet, but yes. What happens is, think of that pancake, you're shooting a bullet through that pancake is thin, you're shooting a bullet through it. The stuff, if I think about what's happened at the end, so the collision has happened, here's a pancake with a hole in it going this way. Here is the fragments of the deuteron going this way, and whatever stuff I've made is strung out on a string in between the two of them. This is the transverse direction, but there's no transverse extent to it. So now you produce the hard scattering, but well, unless it's going, unless you produce a jet that was going in the forward direction that stays with the nucleus, it won't be quenched. And you don't look at those. You look at the ones that come off at 90 degrees. Okay, let me just state the last piece of the logic. How do I know that it's parton energy loss? Maybe what happens is that hard quark turns into a bunch of hadrons inside the medium, and the hadrons get slowed down. And the reason we know that is the last piece of the experimental data is that RAA is the same for all hadrons for which it's been measured. So pions, kaons, protons, RA, lambdas even, RA is the same. And that means that all of those different hadrons would have different cross-sections for interaction with the medium. So if what was happening was not parton energy loss, but if what was happening was loss of energy of hadrons moving through the medium, you would see different effects for different hadrons. But the idea here is that what's happening is that the parton, before it turns into hadrons, the parton is going through the medium and it's losing energy. There was a question which I cut off. Yes?
Sorry to go back, but peripheral collisions, why do we see no jet quenching?
Because first of all, it's an experimental fact. That's the important thing. The idea is that if the collisions are peripheral, you have something like this with a relatively thin almond. The hard scattering has to have occurred somewhere here, and there's no way that the most medium that this hard parton that's produced can travel through. Remember, these spectators here are way down the beam pipe that way. These spectators here are way down the beam pipe that way. The stuff that you make in the collision is only here, and so there's no distance for it to travel through. It's the same reason why you don't see it in deuteron gold or in PP. Yes? The data that I showed you is not, but the initial data in 2003-04 was not, but by now it is. Did you say which parton or which hadron? I'm sorry. Which what? Parton. No. There's no way of separating, no practical way of separating quark jets from gluon jets on an event-by-event basis. You can try and do so statistically, but no one's ever tried that in heavy ion collisions. It's hard enough to do in proton-proton collisions. There's long discussions as to whether you can. It's not easy, and I'm no expert. So the short answer is no. Yes? It's a bunch of hadrons flying down the beam pipe.
It's not a nucleus form.
No, the nucleus is typically broken up in, there are, in all the RHIC experiments, there are what are called 0-degree calorimeters. Okay? That beam pipe, it goes, remember, the curvature at RHIC is a certain number of kilometers around, the beam pipe is curving. You go far enough this way that the beam pipe is curved a little bit, and you put a detector right here. All the RHIC experiments have these 0-degree calorimeters. So there is actually data on the distribution of fragment sizes of the spectators, but I'm not aware of why that data is interesting. So I don't have it in my head. I could tell you offline why those detectors were put in place. It's an interesting story.
Why does energy loss from partons imply that RA is
Because the idea then is that the parton loses energy before it fragments into hadrons. So it loses a bunch of energy, then it comes out of the medium. Let's suppose it still has enough energy that it comes out as a, okay. So we're going to talk about data. We only have data from RHIC, but this is all going to be done at the LHC, as I was going to mention in a few minutes. At the LHC, the partons we'll be talking about are 200 GeV partons. A 200 GeV parton is not going to be quenched. Nobody expects that. A 200 GeV parton might come out as a 100 GeV parton, but it won't come out. It won't be stopped. So let's use that example. So then the idea is that this 200 GeV parton loses energy, comes out as a 100 GeV parton, and it turns into hadrons after it's already outside. So it turns into hadrons in the same way that a 100 GeV parton always does. And RAA, remember, RAA is always normalized by what you measure in PP collisions. So this says that the parton turns into hadrons the way it always does. Okay, so how do we theorists, not yet quite we theorists, but how do theorists analyze jet quenching? This would be a course unto itself. I will try and give you a flavor. And, of course, the question you're asking is what can ADS-CFT do for this story? And that's where I will try and get as quickly as I can. Where's my chalk? Here. Okay. So the basic picture is that I have a hard parton with energy E. And if you open Jackson and ask, let me ask about the analog thing in electromagnetism. Okay, so I have an electron moving through matter, and you can read there's lots of subsections of Jackson about energy loss of electrons in matter. There might be it probably appears in different chapters even, and there are different mechanisms by which electrons lose energy in matter. But in the high energy limit, the answer is Bremsstrahlung, and the same thing is true in QCD, as was first shown by a set of authors, including Miklos Iliassi, in the early 90s. So the dominant energy loss process in the high energy limit is a process in which this parton with energy E loses some energy. And so out here I have a parton with energy 1 minus x times E. This carries off energy x times E. And this has some transverse momentum kT. Now I mean transverse relative to this direction. And so if this was the end of the story, you would say this one has exactly the equal and opposite transverse momentum. But this is not the end of the story, because this whole thing is happening in a medium. All of these hard particles are repeatedly interacting softly with the medium. They're all being jiggled. That's the picture. And so what that means is that this one has some transverse momentum which is of order kT, but it's not exactly the same as this one because they've been jiggled differently. And the statement from a decade's worth of literature that begins in the early 90s is that if the energy is much bigger than the kT of the radiated gluon, which in turn is much bigger than the low scales in the problem, which are the temperature and lambda QCD. So the theoretical treatment that I'm going to give you a cartoon of requires a double separation of scales. The jet energy, the parton energy has to be much larger than the kT of the radiated gluon, which in turn has to be much larger than T. And if you think about this at RHIC, I showed you plots that went out to about 20 GeV. Maybe you can even get, maybe that 20 GeV pion came from a 30 GeV parton. And the temperatures at RHIC, well, maybe we should put pi T here, because those are the typical momenta of particles in the collision, of particles in the Quark-Gluon plasma, if you think wrongly in a quasi-particle picture. And so this might be, I don't know, 0.5 to 1 GeV, loosely speaking. And now you need 2 double greater than signs between this and this. So this framework that I'm describing is a little dubious at RHIC. At the LHC, the nice thing is that this will go up by a factor which is 1.5 to 2. The temperature at the LHC is not going to be larger by more than a factor of 2 relative to RHIC. And this is going to go up by a factor which is bigger than 10. People talk about 200 and 300 GeV jets at the LHC. So the separation between this and this is going to go up at the LHC. So the theoretical analyses that I'm describing are better at the LHC, will be better at the LHC. But we do what we can. So really, if you ask what are people in the heavy ion community excited about the LHC for, it's not so much that the Quark-Gluon plasma will be a factor of 2 hotter. That's what you always tell the New York Times reporter. We're going to make a hotter Quark-Gluon plasma. Because the New York Times reporter doesn't come back and ask you, why should the plasma be interestingly different if it's 2 times hotter? And I don't, maybe it will be. Maybe it'll be all of a sudden a weakly coupled gas. There are theorists who say that it will be, but I don't believe it. I think it'll be similar. But what will be interesting at the LHC is that you'll be probing it with much higher energy particles whose production cross-sections are much better described perturbatively. All of this physics that I'm describing will be under control at the LHC in a way that it's not at RHIC. Okay, so what do we do now in this calculation? So there's 3 hard particles in this diagram, the white chalk. Each hard particle, each hard parton is being jiggled, and it picks up transverse momentum. And there's a defining a key parameter, a key physical quantity, which for no good reason is called Q hat. And Q hat is the average transverse momentum squared picked up per distance traveled. So it's a measure of how good these orange lines are at jiggling the white lines. So what's really needed, I would say, and some of us are pushing in this direction, as I will also say, is what's called a soft collinear effective theory description of this physics. So soft collinear effective theory is the effective theory that was designed. It wasn't designed for this, but it was designed for other problems in which there's a big separation of scales. So here we have a separation of scales. You would like to have some sort of a factorized description where, at least at leading order, you have physics at this scale, physics at this scale, physics at this scale. You would like to set up an effective theory in which your calculation is controlled by the ratio of this to this and the ratio of this to this. Sorry, I guess the inverse of those ratios. So you'd like to do a calculation which is initially leading order in this ratio and then can be improved to higher orders. And that's what soft collinear effective theory is for. No one has done that yet. No one has succeeded in doing that yet. But what we have right now is 2 things in the literature. We have leading order calculations, which are basically leading order in alpha, which are nobody has shown that they're systematically improvable. So they're leading order and not obviously controlled for this whole story. And then the other thing, which is new since yesterday, is that Hong and I and our graduate student Francesco Deramo posted yesterday on the archive a soft collinear effective theory calculation of Q hat. So in other words, you just look at, say, this part of the story right here. Not the whole story, but just this part of the story. Where I have one, or just as well, this part of the story, or this part of the story, but not the whole story. Where you have one hard particle being jiggled, how much jiggle is there? We showed how to calculate that in a way that I think really is rigorous. So you can read that on the archive. Yes?
So are they the same? Are they using the same tool for Quarks and Gluons?
No, but they differ just by a Casimir. So we can make this Q hat for a quark, let's say. In the leading order calculations, which are not rigorous, in the leading order calculations that are the result of a decade of work by people like Bayer, Dockschitzer, Al Mueller at Columbia, Jelassi, Jinian Wang, Urs Wiedemann, Zakharov, many others from the QCD community, you find that Q hat actually controls the energy loss rate. and this is not obvious, but it's the result. You can read long papers by the folks that I just listed. And what you find at the end is that the spectra of radiated gluons, so in other words, what's the distribution of XE there? I'm going to call XE, I'm going to call omega. What's the distribution of omega? Omega di, the omega goes something like alpha times the square root of q hat over omega times L for omega is less than q hat times L squared. And there's a lot of physics in that result, which is all QCD physics, and it's good stuff, but it has I want you to take it on faith. And actually, what I really want is for it to be redone in a rigorous calculation, and that's what Hong and I, wherever Hong is sitting. Where did I see you, Hong? Oh, he just disappeared. That's what Hong and I are trying to do. That's what Francesco Deramo et al. Are trying to do. So we'd like to check a result like this in a more rigorous way. Once you have the spectrum of radiated gluons, you can integrate it up, get the energy loss rate, and there's a long calculation, a lot of phenomenology that has to be done, in which you start with PT spectra. So this is number of pions versus P transverse momentum. And here's that spectrum I showed you before. This is from PP. You calculate how much energy each one loses. They each lose energy. You get some new spectrum, which is lower than the old one. That's the RAA suppression. And you can do this whole calculation and compute an RAA. And I've just summarized many person years worth of work. But everything has been done in terms of a parameter q hat. So how might one calculate q hat? Well, the first thing you can do is calculate it by pretending that the quark-gluon plasma is weakly coupled. If you pretend that, so if you make the assumption that we now know is bad, so if alpha s at t were small, then q hat turns out to be, well, it's proportional to the entropy density times alpha squared. And this is the number density of scatterers. This result makes perfect sense. The entropy density in a weakly coupled plasma, it counts the number density of particles. And q hat is the jiggle you pick up per distance traveled, so that'll be proportional to the number density of scatterers. Alpha squared is the dimensionless measure of the scattering cross-section. It's the piece of the scattering. It's what it comes in here from the scattering cross-section. And when you put numbers in, this becomes 3.1 times alpha squared nc squared t cubed, and I highlight in particular the nc squared in the result. That comes from the entropy density. It comes from the fact that you're counting scatterers, and when you put numbers in, this turns out to be 1 GeV squared per Fermi. And actually, there's a work in here because the temperature, of course, is a decreasing function of time. You have to do the appropriate average over that decreasing function of time. So I sort of lied here. This was q hat as a function of temperature. This is a time-averaged q hat. But anyway, just let me do it. So then you go and ask, what do you get from data? And the way you do this is you do the so you think in your theoretical calculation, q hat is now a parameter. You don't try and calculate it. You just let it propagate through your calculation. What you do is you calculate RAA of PT. And remember that the data was down here. And you put in a q hat, which is too small, and you get something like this. You put in a q hat, which is too big, you get something like this. You put in a q hat, which is just right, and you go through the data. That's the idea. And what you get is, by comparing a theoretical calculation that has all the physics I tried to sketch in words, you get a Q hat which is around 13 plus 6 minus 5 GeV squared per Fermi. And you can see that it's significantly larger than this. You can also see that the extraction is still uncertain. The extraction is going to get better at the LHC. And the other thing that will get better at the LHC is the systematic, if you like, the theoretical systematic uncertainty. And what I mean by this is that the biggest caveat is what I've been describing here is radiative energy loss, Bremsstrahlung, is only the whole story. For E much, much bigger than KT, much, much bigger than T. And that's not necessarily true at RHIC. That will be a much better guess at the LHC. So but what this calls out for is a strong coupling calculation of Q hat. So the picture here is we are going to assume that alpha S at the scale KT is perturbative. And we're certainly going to assume that alpha S at the scale E is perturbative. If we don't make those assumptions, we can't even get started. Just a second, Michael. But we don't want to assume that the plasma itself is weakly coupled. If we do assume the plasma is weakly coupled, we get a Q hat that's too small. So we'd like a strong coupling calculation of the physics at the scale T. And that's what we're going to use ADS-CFT for. Yes? So what's wanted then, N equals 4 super-Yang-Mills theory doesn't have jets, doesn't have hadrons, it doesn't have a Quark-Gluon plasma. It has a Quark-Gluon plasma, but it doesn't have a transition. It doesn't have lots of the things that you need to describe the whole story here in QCD. But it turns out, as I'll now describe, that you can do a calculation of Q hat in N equals 4 super-Yang-Mills theory. Okay. But we're still not quite there yet, because I have to relate Q hat to a gauge invariant quantity that you could go calculate in any field theory, N equals 4 super-Yang-Mills or other. So the first people to attempt to do what I'm about to do were me, Hong, and Urs Wiedemann in 2005. I think we made a good attempt. You can go read our 2005 paper. It has lots of citations. But we glossed over some, as it turns out, interesting details, all of which I think we've now ironed out in the paper we posted yesterday. So I'll describe this to you as it's described in the paper posted yesterday. So we want to calculate Q hat. The first part of the story, so the process we're calculating is just this part of the process. And the first, we are going to use SCET, or we used, to show the following, to show that the probability. So here I have KT equals 0 by definition. Out here, I'm going to have some probability distribution of KT. Because you repeat this experiment over and over again, you'll get different KTs each time. There's some probability distribution of KTs. That's what we calculated. And we showed that it's the Fourier transform of something that you will know how to calculate in ADS-CFT. So it's the Fourier transform in the transverse plane by K perp dot X perp of the following quantity. 1 over NC, expectation value of the trace, W dagger at X perp, W at 0. So the angle brackets mean thermal ensemble average. The trace means trace. And these W's are Wilson lines. What are they? So what is W of x perp is a light-like Wilson line at perpendicular location x perp. So here is, this is W of 0, and this is W dagger of x perp. It's a little hard to draw. If I think of this, the board as the t and z plane, this one should actually be a little out of the board. It's displaced in the transverse direction. Okay, they're both light-like Wilson lines. They're infinite in extent. It's a QCD calculation to show this formula. And then, so all we need from ADS-CFT is the calculation of this. So this I'm going to define, as we did in our paper, as curly W of x perp. And now the key thing, the thing that we missed in 2005, is that the operator ordering here is not time ordering.
I'm still trying to understand the geometry here. So that's D2. So you have a jet going this way.
There's no jet anymore. I've abstracted away from the jet. But yeah, you can think of it. There was, yeah. I mean, on the board there's a Wilson line at this point. But yeah, there's a jet going this way. This is time, and this is z. And this, I didn't draw it right. It should be a little out of the board in the x or the y direction, the perpendicular direction.
X perp is T and Z.
X perp is y and z. X perp is y. Sorry, x and y. I didn't say that right. X and y. Okay, so
the average is in a 3 plus 1 dimensional isotropic medium.
Correct. But the Wilson line picks a direction. I mean, it's a Wilson line that's going in a particular direction. So I'm going to define coordinates relative to the direction of the Wilson line. The jet picked a direction, if you like. How do you what? Sorry.
Like the Wilson line W0 is just one line of the jet.
You can think of it that way. That's fast and loose. But yes, I'll just say yes. Actually, a better way of saying it is the following. We do this calculation by an optical theorem. So in the actual calculation, there's a product of a matrix of an amplitude and an amplitude star, and this is where the radiated gluon is in the amplitude, and this is where it is in the amplitude star. And in effect, what you're calculating here is you're summing up all possible diagrams in which the radiated gluon occurs at slightly different transverse positions. And anyway, but that's all what went into this calculation.
Normally, I think of Wilson lines in space. So this is a polygon group and a Wilson line.
Exactly. So this is light-like. It's a light-like Wilson line. It's not space-like or time-like. It's light-like. Joe.
This is like every day you will screen W when they get close, but you don't want that because it's physically colored fundamental, not a color symbol.
When this curly W, when x perp goes to 0, this does become 1.
It does become 1.
Yes, I want that. You'll see. Yeah, well, anyway, I'll write the result down on the board in just a second. Okay, but there's one key subtlety which we missed in 2005, and that is that if this was an ordinary Wilson loop, suppose I close it as a loop at the two ends, then the color matrices would be path ordered, but the operators would be time ordered. That's a conventional Wilson loop. This turns out not to be a conventional Wilson loop. So I have to write in words here where the operators are path ordered. And Son has saved me 5 minutes by doing a nice explanation of Schwinger-Keldysh. And so what that means is that what we were doing in 2005 is that we were putting both Wilson lines on this contour, but we shouldn't have been doing that. If you like, W should be here, and W dagger should be here. We want this extent to be epsilon, to be infinitesimal. So this is, if you like, this is this is the imaginary time direction. And you have epsilon, they're epsilon apart. And so what Son called sigma, we're going to take to be epsilonic. Because we're using this epsilon as a device to enforce the correct operator ordering. We want all the operators in W to come first, and then all the operators in W dagger to come later when you do the path integral. And that is then when this is the advantage of doing things rigorously. You discover new things. When we did things a little in the heat of the moment in 2005, we and everybody else missed this. Actually, that's not quite fair. We missed it. Various people suggested to us that maybe we had missed it. It took us 5 years to agree with those various people. Yes. It probably wouldn't make any difference, but I'd rather think of it as two infinite lines. But probably I'm not going to prevent you from doing that, I don't think. Okay. And what is Q hat? So P of K perp, I've just told you how to calculate Q hat, or to write in terms of a Wilson loop. Q hat is then 1 over L integral d2K perp over these 2 pi squareds are conventional. K perp squared P of K perp. Because remember, this is equal to the mean of K perp squared over L, and that's what I just wrote here. So the dear string theorists, please calculate this Wilson line, or this pair of Wilson lines. I will then Fourier transform it. I'll do an integral, and I'll get Q hat. Yes?
How do you establish this result? And secondly, why?
Which result? Which part?
Well, the top line, P equals straight.
It's about 10 pages of 2-column PRD format.
Also, why is it gauge invariant?
It's gauge invariant because we take the Wilson lines to be infinitely long.
So you're imposing some boundary conditions on each.
Yeah, and we don't really care about them because we're only so we're taking a limit in which infinity is far away. We're taking a limit in which I don't care about end effects. Okay, what I care about is the contribution from the long lines, not whatever you do at the ends. I don't care about. Right. Okay. So let me now just remind you in sketch form of how Maldacena taught us to calculate Wilson loops in n equals 4 super Yang-Mills theory. He said in n equals 4 super Yang-Mills theory we have a boundary. And well, we're at non-zero temperature, so down here there's a horizon. This is the fifth coordinate, which has been called R or Z, no doubt, in various different lectures. And the prescription is on the boundary, put your Wilson lines on the boundary. So here are my Wilson lines. And think of these Wilson lines as endpoints of a quark. Let a string hang down below that quark. That string will describe a world sheet, which sort of looks like this. So the picture you should have in your head is 2 rails here with a bed sheet hanging from them. And you then define the Nambu-Goto action of that string world sheet, which I will write down just to establish conventions. So this is, has this been described? Joe, did you talk about this? Okay. So these are world sheet coordinates of the square root of minus the determinant of little g, where little g is the induced metric on the world sheet, so g alpha beta. So alpha and beta are world sheet indices. Gmn d alpha xm d beta xm. So this is the ADS black hole with metric big GMN. And so this curved metric big GMN induces a certain metric on the 2-dimensional world sheet. You integrate that. That's the action, the Nambu-Goto action. And the prescription is that this thing that we're after, W of x perp, is equal to e to the I s, where s is this action. And this action for this world sheet So when these are light-like, it turns out that this world sheet in the bulk is space-like. And so this S is imaginary. So this will be e to the minus real. And I thought I would switch now to the screen. So I need to dim some lights here, right? Where's the front? That's probably enough, right? Hello. There we go. Okay. I don't know if you can see that, but that's just for fun. That's a picture of a heavy ion collision. That's 2,000 tracks in the star detector. Oops. Okay. So there, by the way, again, just once to show you real data, that's the missing away side jet. That's the angular correlation function I described first. That's the one I described second. There's all the hard particles. All of the hard particles have turned into a bunch of extra soft particles, which are the blue stars. And you see that there's some hint of an excess indicated by those blue arrows up there at here and here. That's the control experiment. And this is what I described 5 minutes ago. This is RAA versus PT, and this is what you get if you make too small a Q-hat choice. This is too big a Q-hat choice. This is just right. And the experimentalists did this, so they gave us a likelihood plot for the values of Q-hat, and that's the result that I quoted. Okay, now here's my bedsheet diagram. So this is what I was just describing, and the subtlety is that this line, this rail here, is at a real time, and this line here is at t going from t equals 0 up to t equals minus z. Here's t equals 0 minus I epsilon, t equals minus z minus I epsilon. So we have to put this rail at a slightly imaginary time, whereas this rail is at a real time. And what that means in the diagram that Son so conveniently drew, this is the Euclidean time black hole. This is the real time black hole. So let's say we're drawing where is that string world sheet at this value of the real time. Then the red half of the world sheet has to be slightly displaced in imaginary time. And you should think of this imaginary time disk. So if you think of imaginary time as coming out of the board in this left-hand diagram, so look at that diagram. It's like this. Think of that disk as coming out of the board. So the world sheet is slightly displaced. Anyway, that's the calculation you do. Right. Sorry, I didn't say. It's at the end of the day, the calculation you do is like the catenary calculation of classical mechanics. You have to extremize this surface, and this is sort of a loose. This is a cartoon of the shape that you find. It's actually not a bad cartoon, but it's not precisely a catenary. Yes. So that's so. In 2005, when we did this calculation, we were not doing this subtle thing here. We were not aware of these epsilons. And we found, just by calculation result, we just followed our nose and we extremized, and we found that the sheet kisses the horizon. It's tangent to the horizon. It doesn't go inside it, but it's tangent to it. And now you see, that has to be. Because if you look at this in imaginary time, one half of the sheet is at a slightly different position in imaginary time than the other. And the only place where time t equals 0 and time t equals minus I epsilon meet is at the horizon, okay, because of this disk structure which Son described. So the only way that this green half of the world sheet can connect onto the red is if it goes down to the horizon. So we now have an explanation for what in 2005 was a result of calculation. Okay, so what's the result when you do this? I will put it on the board, which means leave the screen there, but let me put the spots up. Those are the wrong ones. Upper house. It's a very nice and simple result. P of k perp turns out to be a Gaussian. So you get diffusion. So what you find when you do this result is that when you do this calculation, is that W of x perp turns out to be e to the minus 1 over 4 root 2 q hat L minus, where L minus is, well, I mean, I could just call it L, then I'm just off by a root 2. I think when I get L, I shouldn't do that. If L minus here is the length along the light count, so it's root 2 times L. So there'd be an 8 here if I made this L x perp squared. So this is the result of the calculation, where I have to tell you what q hat is, where q hat turns out to be, determined analytically, it's pi to the 3/2 gamma of 3/4 over gamma of 5/4 times the square root of lambda times t cubed. Lambda is the Atoff coupling. And now, so I said, dear string theorists, please tell me this Wilson loop. I'll determine q hat, and I'll determine p of k perp. P of k perp is a Gaussian. Also, it's 4 pi root 2 over q hat L minus e to the minus root 2 k perp squared over q hat L minus. So after this, you shoot the bullet through the Quark-Gluon plasma. It's picked, the distribution, the probability distribution for the transverse event it picks up is Gaussian. And q hat times the distance traveled is the diffusion constant. It's the diffusion constant in momentum space. Okay, so what does this imply for phenomenology? And now I need the lights down. So there's the result for q hat again. People have, in fact, done some work towards calculating the 1 over lambda corrections. No one has done the 1 over nc squared corrections. The important thing in this result is that q hat turns out not to be proportional to the entropy density because it doesn't go like nc squared t cubed. For the person who asked about the fact that it kisses the horizon, it had to go near the horizon. We had a physical argument for that back in 2005. If you're familiar with the way to think about the ADS-CFT correspondence, in which position in the fifth dimension corresponds to energy scale in the gauge theory, q hat is sensitive to physics at the scale t. That means this bedsheet has to dip down to somewhere near the horizon. And here you see q hat is proportional, in fact, to t cubed. But it's not proportional to nc squared. It's proportional to the square root of lambda, which is the square root of g squared times nc. And this reminds us that liquids don't have well-defined quasi-particles to talk about. So the real lesson of this for the QCD community is that not the number at the bottom of the slide, although we'll come to that, but the real lesson is that liquids don't have well-defined quasi-particles. So when you think about jet quenching, you shouldn't think about it as scattering off of, you scatter off of here, and then you scatter off of here, and then you scatter off of there. Q hat is a more collective quantity, which turns out to be what it turns out to be. But remember, this is n equals 4 super pi still. We have to talk about getting to QCD. Okay, you try some numbers just for fun. You put nc equals 3, alpha equals 1/2, and you get a q hat, which is 5 GeV squared per Fermi. That's closer to the ballpark of what Rick wants, but even this is still a little bit on the small side. But the data, maybe the data will come down a bit, and in fact, there are some hints that the estimate from data is coming down. So we will wait. The numerical comparison is premature.
Did the change of n scaling, did the change of contour change the n scaling?
No. It actually didn't change anything. What it did is it justified the choices that we made before. The real thing it did is it eliminated various other spurious world sheets that don't go down and kiss the horizon, which we and Philip R. Gyres and various others got distracted by. So it separated the wheat from the chaff. It eliminated chaff, but it didn't change the result. Okay, so well, it would be wonderful if somebody in the audience would come up with a gravity dual for QCD. Of course, that hasn't happened yet. So what you do as a theorist, if you're lucky, like Son was, you might find some result which is valid for any theory with a gravity dual. Q hat is not such a quantity. It couldn't be. It's dimensionful. So you have to ask how Q hat changes as you change the theory. And I'll report here on 2 results. First of all, we investigated a large class of conformal theories, all with gravity duals, and found that for a large class of such CFTs, the ratio of Q hat in the other CFT to Q hat in n equals 4 is the square root of the ratios of their entropy densities. So this further highlights the lesson that Q hat doesn't go like entropy density. This is a little bit of a joke. It's hard to believe this would be a universal quantity, but what it says is that the ratio of that Q hat, if you just take out the square root of lambda and the t cubed, and you take the square root of s, where you take out the nc squared and the t cubed, that this quantity is the same in a large class of conformal theories. It's a very funny looking quantity. I'm not really sure that it is universal, but it is universal in a certain class. And you can then ask, you can be bold and say, well, QCD is not conformal, but we know how many degrees of freedom it has. We know the difference between the entropy density in QCD and that in n equals 4, so we take the square root of that, and that turns out to be about 0.63. So that would suggest that the Q hat in QCD is 63%, if you believe that more than you should, of that in n equals 4 superioid But Q hat is not conformal. We don't have a lot of examples of non-conformal theories in which Q hat has been calculated, but there is one toy model in which it's not a theory, it's a model. It's, I'll show you here. I wasn't going to do this, but this was written down by some other people. This is just a metric. They took the ADS black hole metric and they modified it by putting this in front of it, which is a one-parameter deformation of the ADS black hole metric that makes it non-conformal, and it affects the thermodynamics. And you can tweak that one parameter to make the thermodynamics look the way it does in QCD at high temperatures, which is not quite conformal, as I said. And if you tweak that one parameter in that way, it turns out you increase Q hat by 10 to 20%. So the message of this slide is Q hat is not, by itself, is not universal. But when we do the best we can, so here's n equals 4 superioid mils, here's QCD, and maybe we've taken 2 baby steps in directions that are not quite directly towards QCD, but we took sort of a step that way and maybe a step that way. Okay? And Q hat didn't go crazy on us. It went down by 40%, and then it went up by 20%. And the data is still in development also. So this whole story on the data side will be much better at the LHC. Speaking of which, can we make a prediction for the LHC? Yes. We can make a very simple prediction for the LHC, which is that it just comes from the fact that we don't expect the square root. So Q hat goes like the square root of alpha, and not like alpha squared. And the square root of alpha at the LHC, let's agree that that's going to be similar to the square root of alpha at RHIC. And so that means Q hat goes like t cubed. If you follow that through and understand how to time average Q hat over the expansion history, what you predict is that the ratio of Q hats at LHC and RHIC should be the ratio of multiplicities. And this right-hand side will be measured this November on the first day of heavy ion collisions at the LHC. So as soon as the experimentalists measure this, we've predicted the ratio of Q hat at the LHC to Q hat at RHIC. Okay. What I wanted to end with is to describe that, I've told you the main story I wanted to tell, but this is not the only way that ADS-CFT, gauge gravity duality, is applied to the physics of parton energy loss. And in particular, at RHIC, this whole separation of scales that I described is not really quantitatively justified. So you might ask, can we treat the whole physics as strongly coupled? Are there ways? So what I described for most of my talk today, most of my lecture today was you treat the high momentum physics as weakly coupled, and you extract this quantity Q hat, which is the strongly coupled physics. You will calculate that with gauge gravity duality. But the other approach, which is due to this list of people here, is to try and do the whole story in gauge gravity duality, but with heavy quarks. So for technical reasons, what you do here is you put in a heavy quark, so with mass m, moving through the plasma, and it turns out that you cannot take the velocity to one limit. This treatment is valid only for masses that are bigger than something here. And you can see here that if I take v goes to 1, I have to take m to infinity. So in other words, if for a certain fixed velocity, you can't take m. You can't take m. You have to take m large enough. For a certain fixed mass, you have to take the velocity small enough. If you're within this regime, there's a very nice calculation, which these authors did for the first time, in which how do you put a heavy quark, one heavy quark, into n equals 4 superioid mils? Here's my boundary again. Down here is the horizon. A heavy quark is trails a string into the bulk, and you take this heavy quark and you move it with a certain velocity, and this string trails behind it. And by calculating, in effect, the Nambu-Goto action of this string, well, from this string's worldsheet, by reading their papers, you learn how to calculate the drag constant. And what you find here is that dp dt, the force on this quark, is minus a drag coefficient times p, where that drag coefficient was calculated by these authors. And you find that there is a diffusion in position space, a jiggle in position space of the motion of this quark. And that jiggle in position space is described by a certain diffusion constant, which can also be calculated, again, by these authors here. And, well, QCD has heavy quarks. There's the charm in the bottom. And there is sort of data on the charm in the bottom. It's not very good data yet, because the way particle physicists identify charm and bottom hadrons is that they look for displaced vertices. You look very close to the collision, you find 100 microns away, there's a displaced vertex, 100 microns away, a millimeter away. And the RHIC detectors don't have microvertex detectors until this year. So Phoenix has just installed its silicon vertex detector. STAR is not far behind. So we will have real measurements of heavy quark physics in heavy ion collisions starting soon, but at the moment we don't. So the poor man's way of detecting heavy quarks is to look for isolated electrons. It is a true fact that most isolated electrons in these conditions come from the decay of either D or B mesons. But first of all, there's most in that sentence, and second of all, there's no way of separating Ds and Bs. So, but you can do RAA for those isolated electrons. You can do V2 for those isolated electrons, and then you can fit those data by a whole series of modeling steps which are built on this diffusion constant. And it works reasonably well, although not great. And it's not clear at the moment whether how much the data are going to shift. So again, you should wait. In this case, wait for the next year or two from RHIC. And then the other thing you can do, so that's the first thing you can do. The second thing you can do, which we can't do in the approach that I described for most of the time, is you can ask, where does the energy go? And what you find is that for that heavy quark, as long as it's moving faster than the speed of sound, it excites a Mach cone. It's like a bullet moving through water or air. And it leaves a wake behind. And this is a calculation done by these folks using methods using gauge gravity duality. So there was a quark moving through the plasma in this direction here. It's currently located there. And as it has moved through the plasma, it has excited a Mach cone, and it has left behind a wake. What you see plotted in this plot is momentum density. So this is motion of the fluid. So here the fluid is moving, here the fluid is moving. If you look at energy density, you actually see only the Mach cone, and that's because in the Mach cone there's compression and heating, and the energy density is extra sensitive to compression and heating because the specific heat is proportional to NC squared. So when you look in the energy density, you preferentially see places where heating has occurred. When you look at the momentum flow, you see anywhere where the fluid is moving, whether or not it's compressed. So here there's a wake with no compression. Here there's a Mach cone with compression. And the reason that this is interesting is you'll remember that I showed you way back here. Sorry, I don't know if I should do this or not. It's too late now. I'm doing it. Way back here, there were these shoulders. Not statistically significant, but shoulders. And what does this look like? Well, remember, there was a hard particle going towards that gentleman, and that angle corresponds to about this angle. It's like a Mercedes-Benz. You rotate around, it's a cone. So many people are intrigued by the possibility that this might represent a Mach cone. But what I would say is if I make the following sociological statement, this might go away. As this is a relatively old slide, and as you look at more and more recent data, this is getting less significant, not more. So I wouldn't hang your hat on the statement that a Mach cone has been discovered, but there are hints of a Mach cone in the data. There are also other interpretations of those shoulders. But again, coming back to the theoretical lesson, the insight that you get from this is that a point particle does make a Mach cone in a strongly coupled fluid. How do you make Mach cones in terrestrial life? You shoot bullets through air or airplanes through air. You don't make Mach cones by shooting electrons through air. Okay? And what we've now seen is that when you have a strongly coupled quark-gluon plasma, you can make a Mach cone by shooting a quark through it, a point-like particle through it. That is a lesson that you can take away. Whether or not this is being seen in the data is less clear. I will skip that, and this will be where I start tomorrow. So I'll stop there. Joe.
The fact that we can throw companies, I think, do that different by order n squared.
Yes.